Good afternoon. This is C++ features you might not know. And so there is a reason you don't know some of these features. They are not all features are useful, and not all features are definitely something that you should be able to use, in your everyday code. So just keep that in mind. We're going to have a lot of fun. Some are useful. I've tried to show some useful techniques we can use with those features, but yeah, not everything is actually going to be useful. So let's begin. We've got an array, we can index into that array. The array index operator that here is defined by the standard to be equivalent to array. And then we do an addition, and then we dereference that. And addition is commutative. So what this means is that we can also write a 17 plus array. And then we can take the definition backwards and end up with 17 array. So the array index operator is commutative. If we have std array on the other end, we can also index into that, but that is defined to be equivalent to a member function call. And unfortunately, int doesn't define a member function, array index operator, so that one isn't commutative, which is a bit of a shame. When we've got two int literals, a and b, initialized to one, negative one, I never really liked that. That is always, hang on, something messed up here. I never really, hang on, let me make this one full screen again. No, that's not the button. Okay, let me close that panel, try that again. Okay, and I never liked that. That is a bit misaligned here, the layout of the two. However, we can write +1, so in there, and now it's nicely formatted. However, the plus is actually not part of the integer syntax. This is a regular operator, just like the negative one. This is the unary plus. And according to the standard, unary plus requires something that is arithmetic type on enum or pointer, and it simply returns the value unchanged. However, it performs integral promotion. What this means is that it can change the type. For example, if you have an unsigned short s and you write +s, now the resulting type is int. This is due to integral promotion. Whenever you have a type that is smaller than int, when you use unary plus or any other arithmetic operation, it will be promoted to int. So we've converted the unsigned short into an int using unary plus. We can also use unary plus on an enum, then it will first be converted to the underlying type and then do integral promotion on that. So here the result is int. When we have an array, we trigger array to pointer decay. So unary plus on an array is an int star. And when we have a lambda that doesn't capture anything, we can use unary plus to trigger the conversion, implicit conversion to function pointer. So when is that useful? Well, we can convert an unscoped enum to its underlying type. But since C++17, I believe there's also still to underlying, which also works for scoped enums. So there's no need to do that anymore. We can also use that to trigger array to pointer conversion, but that's implicit. But as we've seen, we can use it to convert a lambda to a function pointer. And that is especially useful when we have code like this. So this is a C++11 code. We've got a class that takes a function pointer as argument, and we want to pass it a lambda. That one doesn't compile without unary plus because a lambda cannot be written in that context in C++11. We have to use unary plus to trigger the conversion. So this is a neat trick. However, since C++20, we can just pass in a lambda as template parameter directly. So this has gotten less useful. Another operator is the comma operator. So this is sort of the canonical example of how to use the comma operator. We want to reverse a range by taking an iterator range and then iterating for both sides at the end. So here we do ++ left and then negative right, both in the same operation of the for loop. And this comma right here is the comma operator. So what the comma operator does, it takes a pair of expressions and evaluates them left to right. It then discards the value of the left expression and simply returns the value of the right expression. So whenever you have a context where you can only write a single expression, but you want to write multiple, you can use the comma operator. One such context is the final part here of the for loop. And this is sort of the intended use of the comma operator. However, since fault expressions got introduced, it's gotten a lot more useful. For example, we have here a function that takes a parameter pack and a function, and we want to call the function on each element of the parameter pack in order. And we can use a fault expression over the comma operator for that. So this will expand to function called first element, function called second element, function called third element. And because of the sequencing requirements, they will be strictly evaluated from left to right. So when you want to do an operation on each element of a parameter pack, you can use the comma operator for that. I've written a blog about a couple more fault expression tricks. At that URL, you will also find all links at the end. So if you're interested in more ways you can use fault expressions to manipulate packs, check out this blog post. Operators can be overloaded. And traditionally, we overload stuff like the assignment operator or the comparison operator. Since C++20, you don't actually need to overload not equals, because the compiler has learned that not equals is equivalent to equals and then negating the result. So starting in C++20, you will never need to write not equals ever again, which is, I think, really cool. C++20 also introduced a spaceship operator for relational comparison. We might want to write an iterator or smart pointer, which has dereference and error operators, or an arithmetic type, which has the arithmetic operators. This is all normal. However, we can overload more operators. For example, we can overload logical AND and logical OR. So if you're a custom bool type, you can overload logical AND and logical OR for those. However, they will not short circuit. So usually the built-in ones, they will only evaluate the right-hand side if that is truly necessary. So if you have some logical AND and the left-hand side is already false, there's no need to evaluate the right-hand side because the result is already false. But if it's overloaded, you lose short circuit. So when would you ever overload logical AND or logical OR? Well, the standard library in C++26 is probably going to ship with an overload. So we've got StudSimD, which is essentially enables SIMD programming, and a StudSimD object essentially contains multiple objects of type T. And then you do member-wise arithmetic on them. So you can, when you add two SIMD objects, you will do add each part of the SIMD object. So you can do multiple additions with one instructions. You can also compare two SIMD objects, and this one does not return bool, it returns you a SIMD mask. And essentially it does a pairwise comparison of each element of the SIMD. So if you have SIMD 1, 2, 3, and you compare it with SIMD 2, 2, 2, then the result will be a SIMD mask that contains false, true, false. And SIMD mask has overloaded the logical AND and logical OR operators and so on, because we want to do an element-wise logical AND and logical OR in each one. And here it doesn't actually matter that we lose short circuit behavior, because there isn't anything to short circuit anyway, because we need to compute each individual result of the whole thing, right? Just because one component would have short circuited doesn't mean that the rest would have short circuited either. So we don't actually lose anything by losing the short circuit behavior. Plus, short circuit would involve branches, and in general, like SIMD programming doesn't like branches. So this is actually the intended semantic that we wanted to have here. We can also overload comma. This one is particularly nasty because the standard library might use the comma operator in for loops with your iterators. So if you overload the comma operator from for your custom iterators, you can really annoy your standard library implementers. Because if the standard library calls that, it's not supposed to, so you can file a bug report requiring them to cast everything to void before invoking the comma operator to prevent calling your overloads. So if you want to annoy your standard library implementers, overload comma operator for your iterators. And then there's this operator, the error star operator. Now, what does that one actually do if you don't overload it? It's for member pointers. So if you pointer to a class member, and then you want to access that thing. If you have an object, you can write object.star member pointer, and this will access the member of object. And if you have a pointer to an object, then you can use error star, and this will then dereference the pointer and then access the member. And you can overload it, for example, for smart pointers. So if you have a unique pointer, you can use error star to use it with a member pointer. Except nobody did that. There is no overloaded operator error star for smart pointers in the standard library. This is because apparently nobody cares about member pointers, which is fair enough. And also, like, we don't really lose anything. We can just dereference first and then use dot star. So I guess they didn't find it useful enough to overload. However, I've recently overloaded it because it's useful for one particular thing. So I work at ThinkCell. I take care of our core libraries. And one of the things we have is we have a macro that executes something at scope exit. This is really useful, particularly when you're dealing with a bunch of C APIs. So you want to open a file, and then when on scope exit, you want to close it. So here we've got a file handle, and then we just want to ensure that it's closed on file exit. Yeah, the semicolon needs to be there. So I didn't like the syntax. This was the implementation that we had, and essentially like it takes an expression, wraps that in Lambda, passes that to a function, and then the function is called in a destructor. Nothing unusual here. But I didn't really like the syntax. I wanted a syntax that looked more like that. Now this, see, we write the macro, and then we give it the braces, and then we give it a list of statements. And this almost looks like a language feature, right? So how can we accomplish that syntax? Well, we need to create a guard object, and we need to wrap the result in a lambda. So the last part here is easy. We just need to add that thing, and now that is a lambda. And then we somehow need to add something here that creates a guard object. Well, we can create a text type and then use an overloadable binary operator with high precedence. And all the underlying part is then hidden inside the scope exit macro. So we just need an operator that we can overload. It's binary, and it has very high precedence to make it work. Oh, and if you look at the C++ operator precedence table, this is the beginning. Right here, we've got the error star operator. This is the first binary operator that we can overload. Just gonna leave this table up for a moment because there's going to be, it will be important at the end of the talk. But the idea is that I'm now going to overload the error star operator to get what I want. So I create a scope exit impl as before, takes the function, calls it in the destructor, and then we've got the text type. All it does, it provides an operator overload that takes a function and wraps it in a scope exit impl. And then we can just define the macro by creating a guard object, creating the text type, invoking it, and passing that thing. And now if you just put braces at the end, this will just work. It will create a guard object, and we've got a really nice scope exit macro that we can use. Let's talk about control flow. So else if doesn't actually exist in C++. There is no language construct else if in C++. Here's the proof. This is the grammar for if statements. We've got two forms, an if with a condition and then a statement, and an if with a condition, statement, and else and statement. There is no else. This is everything the standard grammar says about if. But you can obviously write else if. So what is that? Well, this is an else whose statement is another if else. So if you put braces everywhere, this is equivalent to that. We've got an else and whose body is another if else. So there's a common guideline that you should always wrap all statements in the body of an if or while or whatever in braces. But nobody's going to do that consistently because you write else if and not else braces if. So why do we give else if this special treatment? Why do we treat that as if it was a built-in control flow statement, but not anything else, right? Why stop at else if? What about an else switch? So this is a function, it takes an optional, and then we do a bit of pattern matching, right? We've got, if it doesn't have a color, then we return false, else switch, we do something else. So this is as valid as else if. This is the exact same thing, yet nobody formatted like that. But like, if you do that, who needs pattern matching? Well, we all do, desperately. But switch is fun. So let's look at switch. This is a switch statement. We've got multiple cases that then fall through, then we print something, then we break, and then we have a default case. So the first thing you might not know is you can put them in any order. The order doesn't matter. You can even put the default case up front. And this will still only execute if none of the other cases match, right? So it's not order dependent. You can just put it in any order and it will just work. You can even put statements before any case labels. So here we've got a print statement that is never executed because there is no label that jumps to that. But we can just put as many statements as we want here. Why would we want that? Well, there's actually a use case for that. So C++20 makes this sort of function a bit easier. So we've got the scoped enum, and then we want to convert that to a string. And this sort of code is always a bit annoying to write because you have to keep using the name of the enum here. But since C++20, you can use using enum. And this will bring all the enumerator names into scope. So now we can just write case A, case B, case C, instead of the longer foo A, foo B, foo C. But if you put the statement here, the scope is a bit wide, right? It also brings them in scope for the rest of the function. But we just need them inside the switch. So we can put the statement here inside the switch. And now this only affects everything inside the switch and not around the function. And yes, this statement is never going to be actually executed, but this doesn't matter because it doesn't have any runtime impact. It's purely a compile template. So if you look at the using enum paper, I'm actually a co-author on that. But essentially, this was my only contribution. I pointed out that in the examples, you can write the using enum inside the switch instead of up front, which is a bit nicer. I also suggested the syntax. But anyways, back to switch. So we can braces optional. This is a switch without any braces. And then we can have arbitrary many labels because they're not statements, but only a single statement. So if I is 1, 2, or 3, we will print that. And in either case, we will print that statement because that is no longer part of the switch because we do not have any braces. So the switch only contains a single statement. Arbitrary many labels, but only a single statement. It gets worse. We can also sort of combine a switch with other control flow statements. So this is a switch whose single statement is an if-else. And then we've got a case label sort of nested inside the if-else. So if I is 0, we actually jump to that case because there is no label preceding the if condition. So this one is never executed. And with that sort of feature, let's say, people have written the classic, like this is Duff's device. You might have seen this. So this is some C code to implement memcopy. So we want to implement a switch. We want to implement a function that copies bytes from one pointer to another. And for efficiency, we want to do loop enroll. So we want to copy 8 bytes at a time. However, what if the count isn't divisible by 8? Then we've got this remainder to take care of. And using Duff's device, we can sort of write that bit elegantly. So the idea is that we've got a loop here that just copies 8 at a time. And then we sort of collided that with a switch that handles the remainder. So if, let's say, the count isn't divisible by 8, but the remainder 3, then we will start with the switch, jump directly to 3, do 3 copies, and now we're divisible by 8, and can just repeatedly execute the loop until we're exhausted. So this is quite an elegant way to implement memcopy. Another use case is another macro of our company. So we've got a macro switch no default. Instead of switch, you just write switch no default. And all it does is it asserts when we reach the default case. So it's a runtime error if we don't cover all the labels. And the implementation uses a switch without any braces that starts with a default case. And then inside the default case, we've got an if-else. In the if true case, we've got an assertion, and then we've got an else. And the braces here are actually part of the else. So what's going on? So if I is, let's say, 1, we directly jump to that label and execute the switch as normal, right? We just jump inside the else block and have a regular switch. But if we were to trigger the default case, we jump directly to the beginning, execute the if true, and trigger an assertion. So the coworker showed me that macro was really proud because it's quite elegant. Like we're just changing the keyword here, and we've got a switch that doesn't have a default case. And this is all possible because switch is like a really weird language feature. So the standard library has a bunch of integer types of various sizes. It also has the same for floats. So we've got std floaty and std double t. And they are defined to be the smallest or the smallest integer type that is at least as big as float or double, but is the fastest on your hardware. This is usually float or double, but if you're on a system where double is faster than float, then std floaty may be in fact double. Nobody uses them, but they're there. It also has this called floating point environment, which, for example, can be used to control rounding. So we can, there's an enum essentially, it's part of the C library, so it's a macro or something, but we've got different rounding modes. So we've got FE downward, and this specifies that all operations are rounded towards negative infinity. So regardless of sign, we will round down. FE upward does the opposite, it will always round up, regardless of sign. Towards 0 will round positive values down and negative values up. So we always go towards 0. To nearest does what is naively thought of as rounding. So it rounds to the next closest integer. And there's a function to set the current rounding mode, taking one of those 4. There are also various functions for rounding. So one for each rounding mode that will just round a floating point number to the next integer according to something. And then we've got the function nearby int, and this one actually uses the current rounding mode. So if you wanted to round a floating point value, but you really like global variables, you can use .nearby int and then specify the global rounding mode using this set round function. It doesn't actually affect the built-in floating point operations, just various standard library functions like nearby int. So here we've got stdround, which rounds to a nearest function. And then we use nearby int and have set the rounding mode to nearest thing. But one thing to keep in mind is that, well, what actually happens when we round 2.5? Will it round to 3 or will it round to 2? Because it's right in the middle. And the answer is stdround rounds to 3, but nearby int rounds to 2. And this is because for stdround, 0.5 is always rounded up, whereas nearby int with fe to nearest rounds it to the even integer. So 2.5 will be rounded down to 2, but 3.5 will be rounded up to 4. And this is actually the nicer behavior because it eliminates a bit of bias in the rounding mode. But for some reason, this is not what stdround does. So there's a difference there. Part of the floating point environment also are floating point exceptions. So again, there's an enum that lists all the exceptions like division by 0, domain errors like square root of -1, overflow. So you have overflow when you've got a floating point value that is too large. And then we've got underflow, which is when we have a floating point value that is too close to 0. So when it's too close to 0, it will be treated as if it was 0. And this is an underflow operation. So a nitpick you can use to annoy your coworkers, integer underflow doesn't exist. When you have an integer value that is smaller than int min, that is still overflow. Underflow is only an operation for floating points, and it's about values that are too close to 0 to be represented. There also is a function that you can use to raise a floating point exceptions manually. But before you think, oh, well, this throws an exception. No, this is still part of the C library. It sets a global flag, and then you can manually query whether an exception was raised by calling fe test except. So code that uses floating point exceptions looks like that. We first of all, because it's a global flag, we have to clear it. So we clear all exceptions. Then we do the operation, and afterwards we can manually test whether, for example, a division by 0 occurred. So this is useful. Like you can just do a bunch of floating point operations, and then afterwards you can test for exceptions. So here, if we do a division by 0, we will get infinity because 1 divided by 0 is infinity, and then we print division by 0. But what happens if we do 0 divided by 0? What's the result of that? And well, you might think nan, and it's almost right. It's a negative nan, actually. So 0 divided by 0 is negative nan. This is because there are two not the numbers. Not the number has a sign bit. So we've got positive not a number and negative not a number. And for some reason on Intel architectures, 0 divided by 0 always has the sign bit set in the nan. So you will have negative not a number. When I said there were two not a numbers, I lied, there are a lot more. Because not the number is defined by the exponent, and all those bits here on the 32-bit floats, they can be arbitrary. So you will have about 16 million different not a number values on the float, depending on what the bit pattern here and the sign bit. And this is a lot. So luckily, there's a standard library function, nan, that you can use to give it a payload. And then it will give you a not a number that contains that particular payload. So you can manually specify exactly which not a number value you want, depending on what's the value of those bits. I will get to the questions at the end. So this nan with payload is useful in a technique called as nan boxing. So nan boxing, for example, when you write a bytecode interpreter for, let's say, JavaScript, it needs to store each JavaScript value on the stack or something. And JavaScript values are either numbers or some more complex objects. And numbers can be stored in a double. And the objects, then you need to store a pointer. So you can store the pointer value actually in the NaN bits of the double. So if you have a double that is not NaN, then it contains a number. And if you have a double that is NaN, then you can look at the payload, and that is a pointer to the actual JavaScript object. So this is known as NaN boxing, and it's really useful. Again, all links also at the end. So let's have a bit of fun with syntax. If you've been to any C++ conference in the past years, you've known about the east const, west const debate. It's about whether they write const int or int const. And there are a couple of more decisions that you can make. For example, you can write const exp explicit or explicit const exp. Both mean the same thing. You just have to pick one or the other when you write your code. You can also write unsigned int or int unsigned. And this is because the actual grammar talks about the Deckel specifier sequence, which is just a list of Deckel specifiers in any order. So what this means is that you can even write stuff like int type def a, and a is a type def for an int, because the order of Deckel specifiers does not matter. You can have a volatile float that is inline static. You can use east const exp, so an int const exp c, and we actually use that in our company for consistency with east const. So take with that information what you want. Or you can have, this is an unsigned long, but flunk in a thread local and an extern in the middle. So yeah. So maybe to resolve all the east const and west const debates, just sort the declaration specifiers alphabetically, right? So you would write auto const, but constant. So maybe that's a compromise we can adopt, because the order does not matter. After we've got the Deckel specifiers, we've got a declarator. So here we've got a list of declaration specifiers, and then the name, this is a declarator. And there are various kinds of declarators. The philosophy here is that the declarator mirrors the expression syntax. So to declare a pointer, you write star pointer, because if you write star pointer in an expression, this will get you an int. Array10, because if you write array10, you will get an int, right? This is a function that takes an int, and then you call it by writing the function and then giving it an int, and you will get the int back. So you sort of here write the type, and then here you write the expression that you will use to get that type. This is the idea behind C's declaration syntax. Of course, C++ took that, added references, which completely break the entire thing, because you do not write ampersand reference to get a reference. You just write a reference. So C++ broke this entire philosophy, and now it's just a mess. But because this declarator uses expression syntax, you will need parentheses to avoid ambiguity, right? So this is an array of pointers, because you would write it like so. And this will first do the array index and then dereference and then gives you an int. But if you want to have a pointer to an array, you have to use parentheses, right? So star pointer to array, because you will first need to dereference it before you index, right? It just mirrors the expression syntax. So we need parents to resolve ambiguity. But of course, this means that the grammar also allows that. This is an int called parents. It just, you can put parentheses here. And you can put however many parentheses you want, right? The grammar just allows this. So this is a function that takes no argument and returns an int, and we just wrap the function name in a bunch of parents. And this is also why this code that initializes an A to the result of calling B with C isn't actually that. It's a function that takes an object of type B named C, is called A, and returns an int. This is because this parenthesis here is just allowed around the argument name, right? You can put that in the declarator. So this is a function, this is not a function call. This is one reason why we can also initialize using braces, because braces don't suffer from that ambiguity. In a declaration, you can have multiple declarators. So here we've got the declaration specifiers, and now we've got a comma b, and this declares two objects, a and b. You can also declare a pointer, but you need to watch out. The star belongs to the declarator, not to the declaration specifier. So here only a is a pointer and b is not. This is because it really belongs to the name and not to the type, due to the way the grammar works. But here c is a pointer, a and b is not. You can also initialize a variable. So this initializes d to 42. You can also call the default constructor, except oops, that's a function. So e is a function that returns an int and takes no arguments. And because yes, you can just declare functions in the middle of this line. So f is a function that takes an int and returns an int, and we can just declare it in the same line as all our variables. Of course, we can't provide the definition for the function here, so somebody else would need to do that down the line before we can actually call it, but we can just happily forward declare a function. So if you have a bunch of functions that all return the same type, you can declare them in one line using commas. I've seen that once in actual code. It's not nice. You can also write that. Now that is still a function, and it returns a function pointer, which is a really nice syntax. So let's talk about function pointers. This is a declaration of a variable of type function pointer. This is a function pointer that's returned from a function. So f is a function that takes an int, and it returns a function pointer of the same type as the variable. And this is an array, again, of the same type. So this is an array of function pointers. Now, lambdas that don't capture anything are implicitly convertible to function pointers via a conversion operator that the compiler writes. So how do we actually write that conversion operator? Because that syntax isn't valid. You might try something like that. So we've got the name of the function, and then it returns a function pointer, but no, that isn't right either. We can try that. So maybe the operator is in front and the name is empty, and then we've got just the argument list of the conversion operator here, but that one isn't right either. Maybe you try that. So the name is operator int for some reason, and then we return that. And MSVC actually accepts that, but the other compilers look at that and say, no, that's wrong. Because there is no syntax to write a conversion operator to a function pointer. You have to use return type deduction or type def or anything. It's just an oversight in the grammar that there is simply no way to express a conversion operator that returns a function pointer. It's just that the syntax doesn't allow such a type name here, which is really weird. But apparently nobody ever noticed it in the standardization committee. Okay. Now we finally figured out to declare a function pointer, let's use it. So we have a function pointer, we initialize it to the address of a function, and then we call it. Except you don't need to write it that way. You can just write it like so. So instead of taking the address of a function, you can just write the name of the function directly. And you also don't need to dereference the function pointer. You can just use it as if it was a regular function. And this is because when you have a function type t, it can be implicitly converted to a type pointer to t, which is then the address of it. So we don't need the address of operator here because it's implicitly convertible. And when you have a function call, the type needs to be a function or function pointer. So essentially, we will also implicitly dereference the function pointer. So we have a function that is implicitly convertible to its address. All functions are. Which means that when we call the function, we don't need to write the like so, we can also write *f. This will implicitly convert a function to a function pointer to itself, and then we dereference it, and then we call it. But nothing's stopping at one star, because we can do it again and again. After the dereference, we implicitly take the address, dereference it again, or dereference it more, or at a whole bunch of stars. And this is all valid. When you call a function or function pointer, you can add as many stars as you want, because the compiler implicitly converts it back to the address. So do with that information what you want. So we've got declarations, and we want to use them. So we've got a global variable and a function d, and we want to use it. So increment or call. And this one can actually be done inside the scope. So the declarations can be inside of a function. And this doesn't actually affect anything because they are still an external global and a global function. It's just that the visibility of the declaration is now not visible outside. But this is, apart from that, this is equivalent code. It's just that functions other than f cannot access those declarations. And this also, like people always say that static has a bunch of meanings. That is not true in C. In C, static only has a single meaning. So the only difference between a static at file scope and a static at function scope is that the visibility of file local here is only within the function, and there's no way to access it otherwise. But apart from that, it's exactly the same thing. Both declare a global variable with static storage duration that has internal linkage. It's just that we can't access it outside. In C++, there's a difference when it's initialized, but because in C, all initializers have to be constant expressions, this doesn't matter. So it's exactly the same thing. There's just the visibility of file local, and there isn't a distinction between like a static at function scope and a static at file scope. It's the same feature. It's just a consequence of putting declarations in local scope. When we have a function, it can also have a try catch. So this is called a function. So for example, your main often looks like that. You want to try something and then catch all exceptions by entire program. But you can use a function try block, and this allows you to sort of omit the auto braces. You can just write try directly, then have the body of the main, and then add exceptions at the end. And that one, it was designed for member initializers list. So if a constructor with a member initializer list, which may fail, how do you catch that exception? Well, you have to use a function try block. So try, member initializer list, catch, handle the exception. So that is the only way to catch an exception that is thrown in the member initializer list using this weird syntax where you sort of add catch blocks to the end of your constructor. When we have class, we can use struct or class to declare that class. And the only difference is divisibility, right? So in a struct, everything is public, and in a class, everything is private. But there are a couple of other places where you can use struct or class. So this is an enum class. This declares the scoped enum, and this is an enum struct. And this is the exact same thing. We just used a different syntax. So again, there is no difference. Both are scoped enumerations, just that here we use the keyword class and here we use the keyword struct. No difference. Function try blocks are available since C++ 98. They're really old feature. So no difference between enum class or enum struct. We've got a template parameter. We can use typename t, or we can use class t. Can we also use struct t? So in other words, can we write a template like that? So this is, again, the same thing. We just use struct t to get the type parameter. And the answer is yes, this compiles, but it doesn't do what you think it does, because that's the actual use case. So the struct t here means that foo takes an unnamed value parameter of type struct t. So we have to give a struct definition, and then we can pass in an object. Whereas with class t, now t is just a type name. So this is a subtle difference between class t and struct t in template parameters that nobody noticed. It just happened as a side effect of Sten allowing like non-type template parameters, that you can also have the syntax struct t, and this accepts an object, whereas class t accepts a type. So yeah, somebody pointed that out to me on the committee, and like it's really awful. We also have class hierarchies. So you've got a base class and a derived class, and then you want to do a check down cast, and you can use dynamic cast. So if base pointer actually points to derived, at that point. Otherwise, we get none. That's all good. We can also do what's called the side cast. So we derived has two bases, base 1 and base 2. And we've got a pointer to base 1, and we can convert that to a pointer to base 2 by sort of going down to derived and then back up. And again, this is checked. What we can also do is a dynamic cast to void star. And this is something you might not know. So derived, again, still two bases, and we've got a pointer to base 2. And what we want to get from the dynamic cast void star is we get the address of the derived object. So we've got a pointer to the beginning of the base 2 subobject, and what we get is the address of the entire derived object, which is the actual address of the derived object. So we sort of get the address of the most derived type, but type erased. So it's a void star. And that one is useful. For example, when you want to add something like anyref. So this stores a pointer to anything together with the type info. So just like std_any, it just doesn't own the memory. We can construct it by just taking the address of an object and using type ID. This all works. But if you want to have if you have a base object and we want to have an anyref to the most derived actual object, then we have to dynamic cast void star to get the actual address, so we can then safely downcast. Type ID still works, but we cannot take the address of base directly because it might point here and not here. And if you then do a static cast to derived, this would be wrong, right? Because the real address that we need to cast is that one and not that one. So we have to use dynamic cast void star at this point to get the address of the most derived object. You might not like any, so you use union. So this is a union of a couple of events. So we've got an event kind, and then we've got a keyboard event and a mouse click event. And if we look at the actual size of the objects, this will be 3 uint32s because of padding introduced after the tag. So we've got the tag, then a bunch of padding, then we've got the union. And this is annoying because there is enough padding in each individual union element to store the tag. So we could, in principle, bring it down to 2 uint32s by using the padding that's inside the event payload. But we need to have the tag outside because we need to access it regardless of which union member is active, right? You can only access the union member that is active So if you want to read the current tag, we have to put it outside the union. But that's not actually true, because the standard allows an exception. If type T1 is active, you're allowed to read another member of a type T2, provided that it's part of the common initial sequence. And the common initial sequence is just defined. You take the structs, you list all your members, go by it pairwise in order, and if it matches, that is part of the common initial sequence. So what this means in practice is that if you have a union where each alternative starts with a member of the same type, then we can access that member regardless of which union member is active, because they all have the same one, right? So it doesn't matter which one is active, we can just access it. So what this means is that we can just write a union directly, store a tag as one alternative, and then start each payload with the tag itself. And then we can write union.kind regardless of which member is active, because there's always a kind there, right? At the same address in the same position. So we can just access it regardless of which one's active and bring the size of a union down. So if you have a bunch of unions with tags, consider using this. Just put the tag inside each union member, and then you can just access it regardless of which one's active. It might save you a bit of time, a bit of space. While we're at it, this technique can actually be used to create an empty object that doesn't have a default constructor. So there is legal C++ code that can create an object even though this object doesn't have a default constructor or any other constructor for that matter. More on that in this lightning talk, link also at the end. This is useful in old C++ code where lambdas aren't default constructible. So if an empty lambda, you cannot construct it except using this trick, which uses the fact that you can sort of add access members of unions that aren't active. So unions, they're just like classes. They can have visibility specifiers, they can have member functions, they can have constructors, they can have destructors. I've never seen a union with visibility specifiers or member functions, but it's allowed. You can write that if you want. The standard library has a bunch of dynamically sized sequence containers. So we've got vector, dec, list, forward list. We also have vector bool. It behaves differently than vector of anything else. So it's really a separate type that just shares the same name. And then we've got val array. Now val array is interesting. Val array is an actual vector. So you can do arithmetic with val array. So you've got two val arrays, and then you can do member-wise component arithmetic on it. You can also use it as matrices, so you can slice into it, do a sum, and so on. And it's like really useful for math stuff. It has a wide range of mathematical operations, like all the trigonometric functions are available, you've got reductions, and so on. It's implicitly restrict, so the compiler can assume that if you have two val array reference to a function, that they don't alias, and which enables more optimizations. It can use expression templates for even more optimizations, yet nobody uses it. It's in the standard library, but it's been somewhat forgotten and a bit of abandoned. And so the standard library people don't put a lot of effort into optimizing it because nobody uses it. But like in principle, it's there. It can be used. If you need dynamically sized vectors, like actual math vectors, you've got val array for that, maybe. So maybe try it out. Maybe it works for your use case. This is the definition of runtime error. It's one of the exception classes. It essentially just a generic exception. You can give it a string, and yet then you can give the string back. And so here we give it by formatting an error message and throwing it. But there's something odd about this interface. So we're giving it here a temporary string. So it needs to store a copy of that string somewhere. Yet the copy constructor of runtime error is no except. So it can't actually store the copy inside the exception object, because the copy constructor then might need to throw when copying that string around, right? When it's big, it needs to do dynamic memory allocation, which can throw. So how can the copy constructor of runtime error be no except when it needs to store a string? The answer is that runtime error is a ref counted string. So it simply stores the string once, and then each copy increments the ref count. So like it's essentially a shared pointer of a string internally. So if you need a ref counted string, the standard library provides one, just that the interface is a bit weird, right? To get the actual string, you have to call .what and whatever. It doesn't give you the size, but it's there, right? So there's this ref counter string implementation using only standard library facilities and a couple lines of code. So yeah. So when we have exceptions, they're essentially format non-local goto. So we throw here, and then we catch it, and then we do cleanup. Because a regular goto just wouldn't work. Like you cannot do actual goto to jump between functions. But there is non-local goto in the standard library using long jump and short jump. So what we do here is we need to store the label in an object in a global variable. And then before we call the function, we remember the current position in that label. And then we execute the code. And then if we trigger the error, we call long jump and give it that label. And this will jump back to the position where we just called set jump and returns the number that we given it here. So here at the first call, set jump returns 0. So we execute that code. But when we long jump back to it, then we execute this one and do cleanup. And this is essentially a goto that spans function boundaries. So sort of like exceptions only for C code, and the early exception implementation was built on long jump and set jump. But because it doesn't do stack unbinding, so it doesn't call destruct dots, it's not feasible in actual C++ code. But if you want to jump from one function to another for some reason, the facility is there. The implementation is actually really cool because essentially a set jump needs to save all the execution registers of the CPU, and then long jump just restores them, and by that the CPU sort of jumps directly back to where set jump first came from. Again, a blog post link also at the end that discusses an implementation. If you're interested in like some assembly stuff, that's really cool. So let's end this talk by looking at undefined behavior. So we've got a function that takes two ints, a and b, is the undefined behavior when we add them. Well, of course there's integer overflow, right? A and b can trigger integer overflow, which is undefined behavior. Same is true for multiplication, right? So we can also trigger undefined behavior here. And in fact, if we just pick two random integers, we will have overflow essentially guaranteed, because the vast majority of integer pairs trigger undefined behavior when you multiply them, because there aren't that many that are still small enough that can fit in an int. So this function essentially is guaranteed to have undefined behavior with all inputs. Division also has undefined behavior because we have division by 0, right? A divided by 0 for ints is undefined behavior. So we assert that b is not 0. Do we now also have undefined behavior? Is there any undefined behavior in the division operator besides division by 0? The answer is yes. For that, we have to look at 2's complement. So in 2's complement, positive values start with a 0 bit, and then we've got the actual number, and negative values start with a 1, and then we've got the actual number. But what about 0 itself? Well, 0 is considered to be a positive value. It's all zeros, so it starts with 0, which means that negative values go down to negative 128 for 8-bit, but positive values go up to 127. So we've got more negative values than positive values. So what this means is when we divide int min by -1, the result would be int max plus 1, because int min is 1 bigger than int max in absolute values. So division can trigger an integer overflow only with this particular combination of values. So int min divided by -1 can trigger an integer overflow. All other divisions do not trigger integer overflow. So watch out for that. What about modulo? Modulo is the remainder of the division. So can we have integer overflow there? Well, you wouldn't think so, but in fact, int min modulo -1 is also integer overflow. But this is weird because int min is divisible by -1, so the result of the modulo operation is 0. So how can that trigger integer overflow? It can trigger integer overflow because the standard says so. If a divided by b is undefined behavior, then so is a modulo b. So why does the standard say that? Does it hate us? No, it's just practical CPU implementation. So to compute actual modulo, an Intel CPUs use IDIF. And IDIF computes both a divided by b and a modulo b. So if a divided by b is undefined behavior, then necessarily a modulo b has to be the same. On ARM, it's even worse because ARM doesn't have a modulo. So we sort of have to do the division and then we compute the remainder. And if the division already has undefined behavior, then we just cannot compute the remainder. So there is a reason why int min modulo -1 is also undefined behavior. If you look at it in the debugger, though, it gets really confusing because LLDB says we've got a floating point exceptions, which we don't. We've got integers, and then we've got an integer divided by 0, but we're doing a modulo of -1. So this entire error message is just really confusing. I had that last year and spent a significant amount of time to figure out what the hell was actually going on. So I want to end this talk with my favorite C++ question. This is a tweet from Richard Smith a while ago. I believe we also have a poll in the Zoom chat for that. So we've got a piece of code. What does it print? We've got a short A initialized to 1. Short A initialized to 1. And then we use some size of and some index operator. So what does that one actually print? On a system where, let's say, int is 32 bits, as defined in the question. Well, we sort of covered everything in this talk, so let's analyze it. So we've got a string literal, which is an array. Okay, that's straightforward. Then we've got plus A. A is a short. Unary plus does integer promotion. So the type is an int. Okay. Size of returns the std size t. The size of char is 1, and otherwise it's implementation defined. But here we said size of int is 4. So what we're doing is we use the built-in index operator, which is commutative. 4 indexed into the string, 2, 3, 4, 5, 6 indexed to 4. So the result should be 6. And this was also the result of the Twitter poll. So the majority picked 6. And then we've got the results here. I can say anyway. So that was what was Twitter decided. But if we actually try and run the code, this will print 1. So what's going on here? Well, you might not know who Richard Smith is. At the time, Richard Smith was the editor of the C++ standard. So there's a saying that nobody really knows C++. Well, Richard Smith is nobody, like he knows what he's doing. And his questions have layers. And the answers go back to the operator precedence table that I told you to remember. So here it is again. There's a subscript and size of. Size of is a unary operator. Size of is a unary operator with a lower precedence than array subscript. So what this code actually is equivalent to do is not size of and then we index. It's we index and then we do size of. Or in other words, size of parents and then the index operator. And the result of that thing is a char. And the result of size of applied to char is 1. So this is portable code that's guaranteed to result in 1. And the fact that he gave us the platform was a complete red herring, which is why this is my favorite C++ question. So thank you very much for paying attention. We're also hiring, so we're looking for talented C++ people. If you promise me not to use some of the techniques I've shown in this talk, you're welcome to apply. Otherwise, all the links and the slide will be at that URL. Thank you very much. Right. So there are a couple of questions. Should I go over them now, or should we cover them in the Discord, or?
You can cover some of them here.
Okay. So somebody asked about const expr switch. I think there is no proposal about adding a const expr switch to the C++ standards, because I think the resources are meant to, like, this should be part of pattern matching when that is added. Next up, how is ceil double and floor double for downward and upwards? They're the same thing. So the std ceil function and the std floor function do it the same thing as downward upward rounds. They're just guaranteed to always do that and don't depend on the current running mode. So if you call nearby int with downward or upward, that's the same as ceil or floor. Just doesn't affect the global variable. Okay. So we've got a string array make data constant. Right. So so the question about pointers. The const that you've written in the char const star, that is not the same const. So essentially, that const is equivalent to a const iterator, whereas what you've written is a const without underscore iterator. So the const in the iterator example that is if you have written a const. So if you have a const after the star, so if your pointer itself is const, how to explain that? So what this const actually does is the second line, you cannot increment the iterator because the iterator itself is const. But what you can do is you dereference the iterator and modify that because what the iterator points to, that isn't const. Whereas in the first line, you can increment the pointer because the pointer is not const, but what the pointer points to is const. So you can dereference the pointer and then modify that and cannot modify that. So if you want to have the equivalent result for std vector, instead of writing : iterator, you need to write : const iterator. And that is the same as a pointer to const, which is like the reason why people put the const on the right, because it makes it easier with pointer syntax for some reason. But yeah, so maybe that helps. Extend int global. So you cannot initialize. Can you initialize it with extend? Yeah. So I think this is related to the local function declaration. So when you have a function, hang on, there was some way. Hang on, let me find it. No. Almost there. Okay, it was still after that one. I perfectly know the order of my slides. Hang on. Right. So I think this was related to that code. So this declares a global thing inside the function. So what this means is essentially you can access a global that is defined in some other translation unit, but you can only access it within that function because the other functions don't have a declaration for that. So it sort of gives you extra visibility. If another function wants to access it, it needs to also declare it locally for itself. So it's sort of like, yeah, instead of being the global available through an include. So let's say we've got an include that puts in that declaration. It's available only within the function because we only made it available inside there. This is rarely, if ever, needed because this isn't encapsulation because everybody who knows about the name of the type can still access the global variable, but it's a bit more annoying. Yeah, what is the performance trade-off of Velarray? So Velarray is a dynamically sized container, just like std vector. So it involves memory allocation, where std array is statically sized. So if you need, it's essentially a std vector, but we've also overloaded the math operators on it. In C, we can declare a function pointer with adding type def in front of a normal operation. Can we do? Yes. So you can also declare a function pointer by just putting type def in front. That is the same in C as in C++. So yeah, you can also, but as you've seen, you can also put it in the middle because the declarations specify order and it doesn't matter. Okay. That's the question here in Zoom.
Okay. Jonathan, there are a couple of questions in the chat also. I will read out for you.
Yeah.
First question is, can't we use the initializer part of the switch for using like this? So there is a switch and then we have using enum.
Yeah.
And then we have a val. I mean to say we are just after semicolon, we have a val.
Yeah. So the grammar for that is very similar to the grammar for an if statement. I've got that somewhere around. Yeah, so the grammar for a switch also looks, so we've got a switch and then we've got an optional init statement and then we've got a condition. And an init statement is a subset of statements. So for example, it's a statement that declares some form of variable because like some variable with an initializer can be put in here. This also includes regular type defs because a regular type def is just syntactically the same as the variable declaration. But it did not include, for example, stuff like using aliases. So using foo equals bar. That was not part of an init statement. This restriction got lifted, I think, in C++ 23 or 20. for consistency because typedef is allowed. So typedef bar foo was allowed. So I was using foo equals bar not allowed, right? So an init statement got extended to cover something like declarations with initializer, with option initializer plus using. But I don't know whether it was extended to also covering using enum or using namespace or the other forms of using. So there is a grammatical restriction on what an init statement is. I don't think using enum is part of the lifted set, so you cannot use that in there. This meant to be like initialize a variable was the intent of that thing and not arbitrary code in there. Like you can't put another if inside the init statement of an if. And I don't think using enum is on the list. Like there is an argument to add that on there certainly, but I don't think it is part, but I don't know.
Okay, we can just take one last question.
Mm-hmm.
There is a question, why does legally create XXX do to create the no default constructor? I think they are referring to slide 62.
Yeah. Yeah. So the Lightning talk covers that implementation. So this is a function that you can write that takes a type that is empty and has a deleted default constructor and nevertheless creates an object of that type. And this uses some union tricks and some legal reinterpret casts and some other magic, but you can write this function. And this is no undefined behavior, just creates an object of that type.
Okay. I think that's it for the question. Thanks, Jonathan, for introducing us to many of us with the unusual syntax and the forgotten library features.